Hello everyone, welcome again to another tutorial. So in this tutorial we'll be talking about the registers in the CPU. Remember in the last tutorials we talked about the flags and the ALU. So this tutorial will be talking about the registers in the CPU. So I explained earlier that we have when you go to the site we have 15 different registers, and they have different functions they do within the CPU. The accumulator, opcode, conditional code, index, stack, program counter, the memory data, effective address, and so on and so forth. There are a total of 15. So to understand this is the major part of the circuitry. So to understand this you need to combine three things together: the verilog code, the logic sim circuit, and the note given here. So when you go to the site, you have a lot of tables upon tables explaining all these registers and how they function, what controls them, how they receive data, and how they are latched, how they reset, how they pull data, how they read data, and so on and so forth. So we'll continue from this our circuit diagram. Remember this was the ALU, the flag. So we'll be talking about this. I called it the state machine because that the registers is what controls the instruction cycle, and they go is more like a state machine from one state to another until the whole cycle is being completed. So that's where it gets the name state machine. So let's go into this state machine subcircuit and see what's involved in the register. So as you can see, out was what it takes in, and the output, it has a lot of outputs, but we use just very few of them. So let's go into the state machine so you see what is contained within it. So this is what the state machine subcircuit looks like. So one of the first thing you notice that it has something like that looks like two parts. Like, sorry, what's this? It looks like it has two parts. This side is one part, then this side is another part. Yes. So when you go through the website, you find out that each of the registers, these are the registers. Yeah, this is the opcode register. This is the accumulator, this is the conditional code, this is the index register, this is the stack pointer, the program counter, the effective address, the memory data, what again? The interrupt vector register, the address register, the VMA, write memory address, read write. This is where the read-write that controls all the other circuits we've been talking about comes from. This is the address, the CPU address we've been seeing in our previous tutorials. These are where they come from. This is the CPU data, where it's come from. This is the data address. So this is where CPU generates this data, and this is the ALU left and the ALU right. So I encourage you to read the little explanation I have on the website to understand these things. So each of these registers has a multiplexer that selects which particular data it needs at a particular cycle during a particular phase of an instruction cycle. All the registers, it has a multiplexer. So what this multiplexer does is to select for the register what data it needs at a particular time. Now all these multiplexers are controlled by a signal. Now these are how these are where the control signals are generated. The left hand side of this circuit are where the signals are generated. The right hand side are the registers themselves. These are registers themselves. These are where the signals are being generated. So let's just listen carefully while I explain all these things. Now you can see that all these multiplexers, they have a signal coming from the left side. You can see this one where the control is coming from. So when you go to the site, you see where I explain that. Take for instance, this opcode register is controlled by the opcode control signal. This accumulator here, if you follow the wiring, you see that it's controlled by the AC control. The conditional code, follow this wire, you see it has a conditional code control signal. The index register, it has a index code control signal to it. So let's just go down more. The stack pointer multiplexer has a stack SP control. The program counter multiplexer has a PC control. The effective address register has a EA control. So each of those multiplexer has a signal that controls it, the signal that opens and closes it depending on the phase. Now let's talk one thing we've understood is that each of the registers has a multiplexer that chooses data for it, and each of it is controlled by a particular signal. Now, how are these signals generated? When you go through the site, you see how I briefly explain it. Take for instance, we are talking about the accumulator, and I said that the accumulator is controlled used by the AC control signal, which is, you can see this accumulator here. The multiplexer here is being controlled by the AC control signal. Now let's study this AC control signal. Here you see that is a 2-bit. It has a 2-bit address signal. Now when we go to the site, this is the table. So just the way I will explain, let me explain AC control and this opcode. But if I'm able to explain these two, then just know that's how the rest works. So let me just explain this first two. So that AC control signal, you remember, is a 2-bit address signal. So these are, whenever it's 00, it means it is in a condition described as reset AC, and what it does is resets the accumulator. If it's a condition 01, it means load the AC, and what it does is to read the accumulator. If it's in condition 10, it means pull the AC, and which is pulls data from the CPU data into the accumulator. Then if the value is 11, it means latch the AC. So latch means retain the signal. Whenever you are talking of latch means if you have a register like this, you take the output of the register back into the register. It means that's what indicates a latch. That is for a logic sim circuit, but that's what it is in actual real life, because in a register, once the clock clocks, it takes a new input. So if you now take the previous input back as the new input, it means you have successfully latched it. So this table, now I'll just show you this table, how it works for the accumulator here. So this is the accumulator circuit now, and this is the AC control that's controlling this particular multiplexer. So whenever the value is 00, it takes this first signal here, and what is there is 00. It means reset the AC, which is what we have here. When it's 00, reset AC. Now the second when is 01 means load AC, which is the next value on the. So let me zoom in. Load the AC. Let's see what it does, which is after 00, the next one. It loads the accumulator, which is the LU output here. This, you can see where the signal is coming from. This is the output of the LU. After LU has finished calculations, this is the output. So it's loading this output, and that is why they call it load AC. It loads in this output to it. Now the next one is pull AC, which is pulls data from the CPU data into the accumulator. Now let's also check that, which is this next one. Let me highlight it. Now do you see what it does? It pulls data from the CPU data in. sorry, I didn't explain them earlier. The ALU out is the output of the ALU, then this data in is the data that goes into the CPU. Remember all the peripherals we discussed earlier, the IO port and so on and so forth, they all send data to the CPU. So this is where the data comes in, this data in. So depending on what address the CPU is reading for determines which data will make it. So whenever the AC, the accumulator register is in pool AC, that means it's reading that data input into the accumulator, which is what I've highlighted here. Then the last one means latch AC, and you can see what it did. Just as I explained the latch thing, it takes the output of the accumulator back as an input to the accumulator, and that is what is described as latch AC. So this is how every other one here works. Now the opcode register, it has the opcode control bit that controls it, and whenever it's 0 0 means reset OP, when it's 0 1 fetch OP, when it's 1 0 latch OP, when it's 1 1 latch OP. So it is going to latch OP twice. Now let's just confirm just that one for the OP. Now see it here, you see the OP latch here happen twice. Two of the inputs latched the OP. Sorry, the AC, this is the AC latch here, how the AC was latched. So I won't talk about all of them individually. I've already summarized it on the website, each of the registers and their control data, what they do. The address control, these are the values, is a 3-bit, some are 2 bits, some are 3 bits. So these are the mnemonics. You can see there the mnemonics, and this is what they mean. So when the address control is in PCI data, it means save PC, low data, and so on and so forth. So it's through the help of these multiplexers that these control bits select which particular one. This is the program counter. So if the PC control, this is the PC control, you can see how the signal went to the multiplexer here. So depending, if it's 0 0 it means reset PC, it loads 0 0 to the PC. This one, you can see when it's 0 1, it means increment the program counter, and that's the other block. So when it's 0 2 is 0 8 goes, when it's 0 3 it takes this addition, when it's 0 4 it takes this, when it's 0 5 it takes this. Then when it's 0 6 and 0 7, this is the last part of it. You can see how the two of them came from the output of the PC back as an input to the PC. So that is what is described as a latch, how the data is being latched. So this briefly summarizes the registers themselves. Now their control, let's talk about the control bits, how they function. But just note that, okay, maybe I will talk about that later. Then the control bits themselves, let's see how they are being generated. Remember, the control bits are what determines what the register will store. Now the control register, to understand the control register, I have an Excel sheet on my website. So when you are done with this, I also explain the flags and the rest. Now this is the instruction cycle. I won't go through the theory you're explaining it. I have a little explanation, and you can Google it on Wikipedia to understand what it is. The fetch decode execute cycle. Now let me explain it. Let me take it to the beginning. Just like you have your state machine, remember state machine, well, let me use the big sheet on my PC, so that will be better. I have a bigger sheet where I got the one on the website. This is it. Let me if I can okay, I can't expand it, but let me okay. Now, for one full instruction cycle contains 42 phases. For one fetch and decode cycle, the CPU will go through all of these phases. There are 42 actually in number. When you go through the Verilog code, you will see it also. Now, these are the different states. It starts from reset state, reset 1, reset 2, fetch state, decode state, execute state, alt state, BR-bit, branch state. These are all the states. I described them as cycle. So these are all the states here. So whenever the CPU is in any of these states, now these are the control valve values here. This is the AC control, CC control. So whenever the CPU is in a reset state, this is the value of the AC control. Is in reset AC, CC is in reset CC, and so forth till the end. Reset OP, AC left, MD right, and so on till then. Remember, in a state machine, we have a current state and the next state that is coming after it. So the same thing here. These cycles represent the current state, while this here represents the next state that comes after it. So just like we are in a reset state, then the next state is going to be reset 1. So after reset state, we enter this state, reset 1, and the next state after reset 1 is reset 2. Then after reset 2, we enter reset 2 here. After reset 2, we have fetch state. Here we enter fetch state here. So here, this represents the current state, while here represent the next state. And for each of these states contains the value of all the control signals here. That is what is controlled here. So let's take, for instance, when is in a branch state, that means in a branch state the CC control will be in latch CC, the EA control will be in latch EA, the PC control will be in BR-PC. And remember, I told you I've explained all of them. See, I've explained each of the states, what it means, each of the states. So I want to show you how you'll be able to use this sheet. So any state you will see the value of all those control signals, latch MD, latch OP, you see them. You can go to the site and use any of these blocks to find which particular one you want to check and see what it does. Assuming you see MD right, it means load the MDR register. You see bset right, it means load bset ROM data. So those are the values of the control signal, and whatever the control signal is determines what the register will take, because the value of the control signals are fed as the control for the multiplexer. All the multiplexers are controlled by those control signals. Those control signals determines what the register will take. So this actually represents the instruction cycle, and the instruction cycle contains 42 phases. You can see it here. It's 42 actually, because this is not a phase here, this is the header, but it takes the value of 1, so the number was shorted, but it's 42 total. So each phase has a particular value for the control. So what I did was to I just took the whole value. Let's take, for instance, the AC control. I take the whole value here and place it in a ROM. So that is actually what they describe as the program memory. It's just like what a ROM functions. It stores permanent data that always runs. Remember, we've already treated the RAM, the temporary storage, and how it's being used. So this is how the ROM is being used. So I take each of these, the EA control, I take all the values here and store it in a ROM. The IV control, I take all the value here, I store it in a ROM. The ADL control, I take all the values here, store it in a ROM. So I took all of them column by column and store them in a ROM. So that is why here on the circuit you will see they all have a ROM here. All these are ROM in Logisim, the representation. All these are ROMs. You can see all of them are coming from a ROM. All the control signals are stored in a ROM. So all of them, this is the ADR control, this is the ADR ROM, the data control, this is the data control ROM, the left control bit, this is the left control ROM. So all those data on the Excel sheet have been stored in a ROM. You can clean them. The program counter control bit, which controls this program counter here, is the program control ROM. So that is how the relationship there. Now, one complete cycle, the CPU will run through all this from number 1 to number 42. It will go through all these states or phases. It will pass through all these states, going from one state to another, and when it gets to the last state, it goes back to the beginning again. So that is it. When it comes to the last state, it goes back to the beginning state, all afresh. So let me cut this video now. I will resume it immediately.